Calculating coverage area for your cellular signal amplifier is a simple process once you understand the basics. I'll show you how to calculate the coverage area for a building and walk you through an example so you can see how it's done. The first thing you need to do to calculate coverage area is determine your output signal level. You can think of this as a simple math equation. Your incoming signal strength minus all system loss plus the booster and antenna gains equals your signal output. System loss is all the loss from cable runs and accessories. Depending on the cable you are running, there will be a different amount of cable loss. For every 100 feet of Wilson 400 cable, you'll lose 3.5 dB of signal on the 700 and 800 MHz frequencies and 6 dB of signal on the 1900 and 2100 MHz frequencies. RG11 cable has a loss of 4.5 dB per 100 feet on the 700 and 800 MHz frequencies, and 6.5 dB of loss on the 1900 and 2100 MHz frequencies. There is also a loss when using accessories like splitters and adapters. Each of these accessories will state their amount of loss in their specs. You can find this information on our website or in the packaging for the accessory. For example, a 4-way splitter has an additional 6 dB of loss. Add up all of your cable length loss as well as loss from accessories and you'll have your total system loss. Antennas each have a certain amount of gain built right in. The booster also supplies a certain amount of gain. For example, a Yagi donor antenna has 11 dB of gain on the 1900 and 2100 MHz frequencies. Add the gain from the donor and broadcast antennas to that of the booster and you'll have your total system gain. Take your incoming signal, subtract your system loss, and add in system gain, and you've got your output signal level. From here, you'll also need to factor in open air path loss and material absorption. The further signal gets away from the antenna, the weaker it will be. This is called open air path loss. As soon as the signal radiates out of the antenna, 30 to 40 dB of signal is lost, and it continues to get weaker the further it gets away. Within 3 feet of the antenna, you'll lose the 30 to 40 dB I mentioned earlier. At 10 feet, you'll lose about 30 dB more. Every 10 feet further you go, you'll lose about 10 dB of signal. This can vary, of course, but if you use this as a guideline, you'll have a good idea of signal loss due to distance. Walls, ceilings, and other obstructions will absorb the signal as it passes through. We refer to this as material absorption. For example, half-inch drywall will absorb around 2 to 2.4 dB of signal, while a solid wood door will absorb 6 to 12, depending on the frequency. So you'll need to factor in what building materials are used in the building, as well as how many walls or obstructions the signal will have to pass through. If you're passing through only drywall, one broadcast antenna can cover several rooms. Whereas if the walls are brick or concrete, you may need an antenna for each room. You can download this helpful PDF with tables and charts of all of this information at the link in the description. So let's run through an example to see how this all comes together. You'll want to apply this calculation to each of the carrier's frequencies that you will be amplifying to determine the coverage area for each carrier. We'll use a small office and a Pro 70 Plus as our location and amplifier. After doing a site survey, you find that you've got an incoming signal level for carrier A of negative 65 dBm at the site. The Pro 70 Plus comes with a directional donor antenna with an antenna gain of plus 7 dB. In an office space, a dome antenna is ideal. A dome antenna has a gain of 5 dB. This gives us a total antenna gain of plus 12 dBm. We'll run two 50-foot lengths of Wilson 400 cable, one to each antenna. Each run has a loss of 3 dB for a total cable loss of 6 dB. Our booster has a gain of 70 dB. So if we subtract our cable loss from our incoming signal, we've got a negative 71 dBm. Adding in our antenna gain brings us up to a negative 59 dBm. Now add in the booster gain of 70 dB and our final signal output is plus 11 dB. We know that our signal will weaken as it gets further away from the broadcast antenna. With a plus 11 dBm output signal strength, at 3 feet we'll be at negative 19 to negative 24 dBm. At 10 feet, negative 49 to negative 54 dBm, and at 20 feet, negative 56 to negative 61 dBm, depending on the frequency. You can extend this out and calculate that at 50 feet from the antenna, you will have a usable signal of around negative 80 dB. With a 50-foot radius of signal, you are able to cover over 6,000 square feet of space with a dome antenna. Finally, we need to check the material absorption. From our site survey, we know that all of the interior walls are standard drywall. So for each wall, we will subtract 2.4 dB of loss. So even passing through 2 walls, the signal is still usable 2 offices away from the broadcast antenna. This was a simple example to illustrate the basic idea of calculating coverage. As your designs get more complex, you'll just have to add in more elements to the equation. Instead of a single cable run, you'll have to factor in splitter loss and the cable loss for each individual leg. One thing to note as you are calculating more complex amplifier systems is to calculate the loss and gain for each leg you run individually. If you're using a splitter to branch out to multiple broadcast antennas, everything will be the same up to the splitter. Then you'll just need to calculate the losses and gains individually based on the cable lengths and antennas that you choose for each run. I hope this has helped you understand how to calculate coverage area for a building. If you've got any questions, leave those in the comments below or give us a call. We'd be happy to chat with you about them. Check out some of these videos for more great information and subscribe to our channel for new videos every week. Thanks for watching. See you next time.